All right, let's talk about an overview of compilation. So here's a diagram that shows the compilation process and the various stages that occur in it. We start with the source program, which is really a stream of characters. The first thing we do is we scan it, also called lexical analysis, and we group those characters into tokens, which are the smallest meaningful units of the program. Think about things like keywords or identifiers or symbols like plus or minus. This gives us a stream of tokens, and then the parser takes those tokens and organizes them into parse trees, where each element of the tree captures a structure of the programming language. Based on this structure, then, we do semantic analysis and intermediate code generation, and we generate some kind of intermediate form that represents the semantics of the program, like an abstract syntax tree. These three stages are called the front end of the program, and the front end is mostly concerned with taking the input program and figuring out what its meaning is. Looking at the back end of the program, our goal will be to generate the target code that's equivalent to this intermediate representation. Compilers will often first do machine-independent code improvement. So they'll take this intermediate form and transform it into a form that might be more efficient for execution. This modified intermediate form is then the input to target code generation, which gives us code for the target machine. And then we might do some more code improvement to make that code a little bit faster, a little bit more efficient, maybe a little bit smaller. And finally, we get the target language, which might be, again, assembly code or machine code. If we look at an interpreter, it has a similar front end, but we're not really generating target code. And so the back end is replaced with a tree walk routine that essentially executes the program, taking program input as information along the way. Now, in both compilers and interpreters, we have some information along the side called a symbol table, which carries information about the global structure of the program. What are the names of functions? What are the names of classes or types? And makes it available to any stage that needs it. Let's go into more detail on the different stages of a compiler. So the first stage is lexical analysis. Lexical analysis converts an input program into a sequence of tokens. For example, take this sequence, which computes the factorial of the input value, which starts out in x. We might write the program as shown here, but the first thing we want to do when we compile it is transform it into a sequence of tokens. And so you can see this sequence of tokens. We've forgotten everything about the structure of the program. It's just a sequence of little strings, which might be keywords like while, identifiers like x and y, or symbols like greater than or the assignment operator. Next, we parse the program. Parsing will convert the sequence of tokens that we computed in lexing into a parse tree that captures the program structure. So our assignment here, p gets x plus y times 4, might be transformed into the following form. What is this thing at the highest level? Well, it's an assignment, so that's the root of the tree. On the left-hand side of the assignment is p. On the right-hand side is an expression, which is an addition expression. So on the right-hand side of colon equals, we have plus. We are adding x, which is on the left-hand side of the plus, to a multiplication expression on the right-hand side, which multiplies y and 4. And so we have this tree structure that describes the shape of that computation. That's really what goes on in parsing. Next, we have semantic analysis. Semantic analysis is really about capturing the meaning of the program. It gathers data that's necessary for code generation. For example, the symbol table we talked about earlier will link identifiers to information known about them. Is this identifier a type, or a variable, or a class, or a function? And if it's a function, what is the type? What are the inputs? What are the outputs? The semantic analysis will identify semantic errors as well. Some of those might be inappropriate operations. For example, in the diagram shown, we have Eclipse telling us about an error in Java where we have multiplied the string hello by 5, which of course doesn't make any sense. Other kinds of semantic errors might be using a variable before it's defined, calling a subroutine with the wrong number of parameters or the wrong types of arguments. Or we might want to make sure that a function that has a non-void return type always returns a value explicitly. So we don't have, a situation where we're returning from a function, but we don't have the return value. The next stage is intermediate code generation. So this generates intermediate code in forms that are more abstract or maybe closer to the machine than parse trees. One example of a transformation that sometimes happens is transforming a parse tree or an abstract syntax tree into a control flow graph, which shows little blocks of code along with the connections between them, right? So an if statement might branch and go either to a block inside the if that does a computation or to the block after the if. Once we have the code in an intermediate form, we might do code improvement. This is often referred to as optimization, but we don't really get truly optimal code out of it. We just get improved code. Code improvement typically simplifies computations, it eliminates redundancies, and it can make code substantially faster and or smaller. For example, in the code shown here, we have some redundant computations. We're computing x times 4 twice, and also we're doing some multiplications that could be done with a simpler operator. So we can take x times 4 and transform it into a shift, which can be computed more efficiently on most processors. We can eliminate the redundancy by just computing x times 4 or x shift left 2 once. And so we have now shorter and more efficient code. After code improvement, we might do target code generation. So the target code could be different things, right? It could be bytecode in Java, it could be assembly code, which is a readable version of machine code, or it could be the binary machine code itself. Here, we'll traverse the symbol table to assign locations to variables. So we decide where all the data is stored. We traverse the intermediate code to generate output instructions, and we might generate a symbol table that's useful, used by a debugger to show the state of program execution. So if we take the code generated in the last slide, the intermediate code in the last slide, we might generate x86 assembly language as shown on the right. So for comprehension, let's do an exercise. What distinguishes the front end of a compiler from a back end? So the answer is that the compiler's front end is primarily tasked with figuring out the meaning of a program. And as part of doing that, it transforms the source code into an intermediate representation that effectively represents that meaning, such as an abstract syntax tree. The compiler's backend then transforms that intermediate representation into an equivalent target program that can be executed on a machine, perhaps a virtual machine. Summing up the first chapter, programming language design and implementation are closely linked together. Different languages and paradigms represent different trade-offs. More declarative languages might be more close to the problem, more higher level in terms of abstract, whereas sometimes imperative languages might provide more performance. And of course, market forces and what you want to do might also impact the language that you choose. We've looked at two different implementation strategies for languages, compilers and interpreters, and we've looked at some trade-offs between those, where interpreters might be more flexible, might provide better diagnostics, but compilers will provide better performance, except for very small programs that the compiler can get running right away. Compilers are distinguished by fully analyzing the source program and then transforming it substantially into another form. Finally, we hope you'll study programming languages further so that, because it can help you become a better programmer. And we'll pick up on that with the next lesson.